presentation by Mr. Roger Penrose. Let me also remind you that we have simultaneous interpretation into Portuguese and into English. You can go to the bottom bar, click the globe button, and choose Portuguese or English. You'll find this option in this icon. If you're using a phone or tablet, you can click More or the ellipsis sign to choose the language interpretation button and to then choose Portuguese or English. We can start. Thank you. Thank you. Good afternoon, everyone. We hope you're safe and healthy wherever you are. We know we're going through tough times with the pandemic right now. My name is Rogerio Rosenfeld, and I am a professor at the Theoretical Physics Institute at Unesp in São Paulo. I am also a member of the Unesp Publishing House. Today, I'll be the moderator of this event to celebrate the book Shadows of the Mind. A search for the missing science of consciousness, because this is now being officially released in Brazil. It is an honor for us to have Mr. Roger Penrose with us today to deliver a presentation of around 45 minutes regarding this book. After his talk, we're going to have a Q&A session, so please feel free to send those questions through the Q&A box, and we'll pick the best ones. Now, allow me to introduce you to our very, very special guest. Professor Penrose is a mathematician and a theoretic physicist from England. He has a master's in mathematics from Cambridge University, and he's had a lot of achievements in his career. He was hired as a professor at Oxford in 1992, or 73 actually, and he's been extremely active in his studies, as you clearly see. Professor Penrose is a scientist with brilliant intuition, a lot of mathematical knowledge, and many contributions in different fields, as you'll be able to clearly see. He had research in the area of Einstein gravity theory. In 1965, we saw a theorem talking about the existence of black holes that are created because of the compression of a lot of matter due to gravity. In this work, where we saw the existence of black holes, Professor Penrose received half of the Physics Nobel Prize in 2020, over 50 years after the publication of his work. He shared this Nobel Prize with two other scientists who discovered a big black hole in the center of our galaxy. So we saw that in 1965, but this research from 1965 was then evolved into the theorem that is called the Penrose-Hawking theory. Of course, Stephen Hawking and Professor Roger Penrose created it. He also worked with a number of mathematical tools to describe Einstein gravity theory. We have these books called Spinors and Space-Time. He also wrote a book with Stephen Hawking called The Nature of Space and Time. Mr. Penrose contributed to our field in cosmology as well. For example, we have the Penrose diagrams, which are really important in our area. Professor Penrose also developed a model which is called the Cyclic Universe, or the Cyclical Universe. This one hasn't been confirmed yet, but it was developed by Professor Penrose. However, Penrose goes beyond gravitational theory, and I find this really interesting. He's interested in geometry and mathematics. There is the Penrose triangle, and I suggest you look for it in Google because it is really interesting to see it. And Professor Penrose had conversations with Escher himself. Actually, Penrose's works had an impact on Escher's works, with those drawings that seem to challenge the notion of two dimensions. Another important piece of work by him is his discovery of how to cover the floor, for example, with two kinds of tiles. This is what we can find in what we call quasi-crystals in nature. Now let's go deeper into the topic that we have for today. Professor Penrose's father was a professor of human genetics at the University College in London, and he started assessing the possibility of explaining the phenomenon of consciousness using physics and mathematics. This is a really daring endeavor, but with his ambition, he works with Stuart Hameroff to combine subtle aspects of quantum physics, artificial intelligence, and also gravitational theory. And Professor Penrose uses a modified version of quantum theory, which he introduced in 1996, which is important. Penrose wrote 2 books about this. The first one is called The Emperor's New Mind, and the second one is Shadows of the Mind, a search for the missing science of consciousness. So today we are celebrating the release of this second book in Portuguese, Shadows of the Mind. It is fair to say that this theory is controversial and has not been approved by most of our community, but let's give it 55 years, right? Without further ado, I will now hand it over to Professor Penrose. Thank you, Professor.
Is yours.
Well, thank you very much for that introduction. I hope you can hear me. Is this working?
We can hear you.
Good. Now, in this first slide, you will see covers of the 2 books being referred to, The Emperor's New Mind and Shadows of the Mind, which I gather is now being translated or has been translated into Portuguese. I want to describe the general idea which I introduced in The Emperor's New Mind and made more precise or more plausible, perhaps is the right word, I'm not sure how to put it, in Shadows of the Mind. So Shadows of the Mind expresses more closely what my current view is, the things I didn't know when I wrote the book originally. So I'll come to that shortly. But let me move on to indicate, and now let me see if I can get this to work. It doesn't work now. Oh dear. Now, why is this not moving? There we go. Here we have a picture. Well, perhaps the one on the left is more famous. There are 2 professors at Princeton University who were good friends. Einstein is the one on the left, who everybody knows. The one I want to discuss about at the moment is Gödel. This is Kurt Gödel, who was a logician and made a very powerful theorem, which I want to describe the gist of, because it's this theorem which really started me off in the way of thinking which I want to describe. Now, in Gödel's theorem, a way of putting it is the following. We are concerned with natural numbers. By a natural number, I mean 0, 1, 2, 3, 4, a whole number which is not negative. So that is a natural number starting with 0. And one can make statements about natural numbers. A famous one is the theorem due to Lagrange, which says that every natural number is the sum of 4 square numbers. So that's a sort of example. You can talk about all numbers and they may have some property, for example. Now, you might have ways of proving these things. And let us suppose that these follow certain rules, which I'm calling R. The key point about R is that if you have carried these rules out correctly, or whether you have carried them out correctly, this can be checked on a computer. So this is what the kind of rules I'm talking about are rules which could be checked to see whether they are being correctly applied or not by a computer. So that's the key thing about the rules. They're computational rules. And what Gödel shows that whatever these rules are, if these are rules which are supposed to prove things about natural numbers, maybe they will say you go through steps and steps and steps, and you finally, it comes out and says, yes, that statement is true, then you believe it is true. So they're genuine procedures for giving proofs of things about real numbers or at natural numbers. Now, what Gödel shows is that if you have any such system of rules, computational rules, then there is a statement that you can construct out of the rules. I'm calling this G of R. Then this statement is a mathematical statement. So it could be true or it could be false. But what Gödel shows is that if you accept that the rules are, they're true, they give you what are called sound. That is to say, if the rules tell you, yes, it's true, then you believe, yes, it is true. So you've looked at the rules carefully and you decide that if they say you have a proof, these rules tell you that the result is true, then you accept that the result is true. So what Gödel shows is that for any such set of rules R, this statement G of R, you can see by the way it's constructed that if the rules only give you truths, then you know that G of R is true. But not only that, you know it is true, but not provable by the rules of R. Now, this is rather amazing because, well, it says, roughly speaking, I am not provable by means of the rules R. And you can see, you have to see how to make it do that is quite tricky. That's the whole complicated part of Gödel's result. But the key point is that if you believe that the rules R give you truths, then you must believe that G of R is also true. You also have to believe that G of R is not derivable by these rules. Now, when I first learned this, I was stunned. It was absolutely amazing, because what that tells us is that whatever set of rules that you take, so long as you trust them, as long as these are rules that you believe only give you truths, then you can construct a statement which you also believe is true, but which is not obtainable by those rules. So somehow, your belief that the rules R work, that the rules capital R work, tells you something more than just following the rules. So it's telling you that your understanding of the rules gives you more than the following of the rules. Now, this to me was amazing, because it tells us our understanding is not the product of rules. Now, let me say a little bit more about these rules. First of all, there are things you could put on a computer, or a Turing machine is an idealized computer. Now, this picture, this cartoon, is meant to show that a Turing machine is a finite thing. That's the thing in the middle of the picture. And it has a storage space which could be unlimited. So the machine itself is finite. The number of rules that it has to operate with are finite, but you have a potentially unlimited storage. So that is what we mean by a Turing machine. And of course, an ordinary computer would not have an infinite storage, but you could say, well, if you've run out of storage space, you just bring some more in, and so on. But this mathematical concept, which is defined by Turing as what we mean by a computation. So computation can be defined by a finite system of procedures, but with a potentially infinite storage space. Okay, that's all we need to know about it. Now, I'm going to talk about statements about natural numbers, as I said before. Now, how do you prove, the sort of thing you might learn at school, is how do you prove that something is true for all n, such as the Lagrange theorem, which I mentioned? Every natural number is the sum of 4 square numbers. That's a statement about all natural numbers n. One way of doing it, the sort of way you'd learn it at school, is you can establish 2 things. One is it's true for 0. Well, it's certainly the sum of 2 squares. 0 is the sum of 0 and 0, which is each square. So that's certainly true. First of all, you prove it for 0, and then you prove that if it's true for a number n, then it is true for n plus 1. So you can prove 2 things. If it's true for 0, and if it's true for n, then it's true for n plus 1. Those are just 2 things. And that enables you to show that it's true for all n. Now, I'm only giving you this as an example of how you might prove something is true for all n by just proving a finite number of things. So this is an example of what we learn at school, which is called mathematical induction. And there's a thing called piano arithmetic. I won't bother you with that, but that's basically depends on this notion of how you might prove something is true for all n by using this procedure of induction. Now I want to give you a nice example. It's a wonderful example which I learned a long time ago from one of my colleagues at Oxford. And this is a thing called Goodstein's theorem. Now let me try and describe this. It's something which is, it's a bit of a strange theorem, but it can be described by somebody to somebody who doesn't really know much about mathematics. All you have to know is what it means to raise a number to a power. Let me say about this. Okay, Goodstein's theorem operates on natural numbers, and just as an example, I'm going to give you 1077. That's nothing special about that number. I'm just choosing that as an example. Now, first, what you do to that number is you write it in binary, so ones and noughts. So here these are small numbers in purple. That means it's binary. What does that mean? Well, you look where the ones are, and those give you a power of 2, and you look where the zeros are, and then you ignore those. So this number here, which is ones and zeros, is a sum of, well, you can see represented here. It's, I need my glasses for this, 2 to the 10th plus 2 to the 5th plus 2 to the 4th plus 2 squared plus 1. And that's what the ones in the expression tell you which powers are there, and the zeros tell you which powers are not there. So it's a sum of distinct powers of 2. So 2 to the 10th is 2 times 2 times 2 times 2, where you have 10 2s altogether. 2 to the 5th is 2 times 2 times 2 times 2 times 2 is 5 2s altogether. So it's like that. Okay, so you write it down in that form. That's the binary expression. Now you look at the exponents, and you see the first one, that's got a 10 up there. Well, we try to write that in binary also. What's 10? Well, that's 8 plus 2, which is 2 cubed plus 2 to the 1. So that's what it is. You put 2 cubed plus that, and you write that in binary, and so on. You just take the exponents, you write them in binary. And then you look again, you still haven't finished because there's a 3 up there, and that needs 2 to the 2 plus 1. You may have to go up higher than this. In this particular example, you just have to go up 2 steps beyond this, and then you get this expression here, written in terms, simply in terms of powers of 2, including all the exponents. Okay, now what does Goodstein tell you to do? 2 things. Operation A, you look at all these 2s and you replace them all by 3s. So the number has got much, much bigger. Okay, that's all right. What's operation B? Subtract 1. So you take away the 1 at the end, and it doesn't make much difference. Operation A makes the number much, much, much bigger. Operation B just makes it a teeny weeny bit smaller. Operation A, again, you look at all the 3s, you place them by 4s. And then operation B, you subtract 1. It's a little bit trickier now because there's not a handy 1 sitting at the end, but it's just like taking 1 from 1,000. And if you want to take 1 from 1,000, you get 999. Well, this is the same operation here, except you're using 4s instead of 10s. And so when you subtract 1 from this 4 to the 4 up here, you have to write it as this thing here with 3 times 4 to the 3 plus 3 times 4 to the 2 plus 3. See, 3s are the analog of the 9s when you use the ordinary linear scale, but here we're using the 4 scale, and so you've got 3s like this. Okay, so I've subtracted 1. I put them in a different color because they're less than 4, so you leave them like that. But operation A means take all the 4s and replace them by 5s. The 3s you just leave alone, but everything you replace the 4s by 5s. And then you subtract 1, and you just go on and on and on. The numbers get bigger and bigger and bigger. Well, the first one is 1077. The next one is something like 10 to the 40. The next one is something like 10 to the 600. And they get bigger and bigger and bigger and bigger and bigger and bigger. And then they finally come down to 0. This is a sort of hare and the tortoise, if you like, because the hare races ahead, makes these numbers bigger and bigger and bigger. The tortoise subtracts 1 each time, and the tortoise always wins. Very, very remarkable fact. And if you want to, it's useful, you might say, well, take the number 3, and you can try the number 3. It comes down pretty quickly. What about the number 4? Well, I would not recommend doing it on your laptop. I would not recommend doing the mainframe at the university or whatever. I would not recommend using a computer at all. I would recommend using a piece of paper and a pencil and convincing yourself that if you use 4, start instead of 1077, but you start with 4, the number goes up enormously large, but then comes right down to 0 again. Now, the point I want to make about this is that it is true. Goodstein's theorem is true. Remarkable enough, it is true. The number always comes down to 0, no matter how big you start with, and it goes absolutely huge before you get down. And here you see for 1077, you see how much bigger it does get before it finally gets down to 0. Not only is it true, but you cannot prove it by mathematical induction. I gave you this example of mathematical induction, how you might prove something is true for all n, but this doesn't work here. Mathematical induction does not work. And this was proved by 2 mathematicians, Paris and Kirby, and they showed that Goodstein's theorem cannot be proved by mathematical induction. It's still true, and it's possible to see it's true. It's not so easy. You need something if you know something what's called transfinite induction. This was introduced by Cantor, who was a great distinguished mathematician, and he introduced this idea, generalizing the idea of ordinary induction to what's called transfinite induction. Then you can prove Goodstein's theorem is true using that. But the thing I want to make here is, how do we know? Now, you see, going back to the Gödel theorem, you might say, well, Gödel's theorem tells you that if you have some algorithm in your head, well, you see it really showing it can't be any algorithm that someone suggests. And if you know what that algorithm is, and if you know you're using it, and if you know it works, then you can Gödelize it, produce the thing G of R, and you can see something is true which this algorithm does not give you. But how do we know what algorithm we operate according to? If you believe that the brain operates according to some kind of algorithm, we may not know what it is. So it may be that we're using an algorithm that we don't know. So that, I think, would be the normal point of view people would make. And that is why the Gödel theorem does not give you a problem with this. But I'm going to argue that I don't think that's the answer. What Goodstein shows you is that using transfinite induction, I haven't really told you what that is, and I'm not going to because it's a little bit elaborate, but it's the sort of thing you can understand. That is, you don't need to be Cantor to understand why it works. You need to be Cantor perhaps to discover transfinite induction. Well, okay, but that's not the point. The point I'm making is that any mathematician who, you don't have to be, as I say, you don't have to be Cantor, but a decent mathematician who knows his job and knows how to work, or his or her job, I should say, knows how to work with numbers in a sensible way, can see why this works. Now, the cartoon I'm giving you here is trying to show how is it that if we have this algorithm in our heads, which allows us to show that Goodstein's theorem is true, how did that come about? By natural selection. And this cartoon, which is in Shadows of the Mind, I took this picture. The Goodstein theorem is in Shadows of the Mind too. This is an argument I give there, which is to say, how did our intelligence, how we did mathematics, how could it evolve? Well, it's evolved because doing mathematics is really sort of formalized common sense, if you like. You realize it works because you understand it. And how did understanding evolve? Well, I show you various things. I've shown you in the distance we have our ancestors here are growing crops. They are domesticating animals. They're maybe going in here in the foreground, we see they've discovered how to make a mammoth trap. And all these things are things which clearly were good for developing our capabilities of understanding. It was not sophisticated mathematics, because somebody in the foreground, this poor mathematician here, is developing some theorem. There's a little bit joke about the theorem itself, which I won't tell you, but there is a bit of a joke about the theorem. But the main point is this mathematician developing mathematical ideas is about to be devoured by this saber-toothed tiger. Well, I'm trying to say that there is no selective advantage in doing sophisticated mathematics. So there was not the idea of Cantor's transfinite arithmetic idea, that sort of thing, was not evolved as an algorithm in our heads because it had no selective advantage whatsoever. None of these things were any use in developing the things that we were good at doing. However, a general idea of understanding, whatever that means. And what I'm saying is that understanding, whatever that means, is something which is not algorithmic. It's understanding which enables you to transcend the procedures that were given by this algorithm R, which I gave you in the Gödel theorem. You can transcend R by simply understanding what it means. And what it means has to do with your understanding. And understanding is something that requires consciousness. I'm not claiming to be able to say very much about consciousness in general. And this is a point people often attack me. They say, well, you're not saying about consciousness, and lots of consciousness has to do with other things, even such perceiving the color blue, for instance. That is something which requires consciousness. How do you know what blue is like? Well, you perceive it, and that's a conscious experience. It's not what I'm talking about. Consciousness involves lots and lots of other things than understanding, but I'm only concentrating on understanding merely because that's what I can say something about. I can't say anything about perceiving the blueness of the color blue, for example. It's something very subtle, and certainly people with certain conditions get confused about blue, and the color, perceiving colors get mixed up with smells and things like this. And synesthesia, there's a condition that some people have. That's a very interesting question. It's not the question I'm concerned with. I'm concerned with the question of understanding. And I claim that understanding is something which is not an algorithm. And that goes back to the argument which I gave about Gödel's theorem. Now, I want to say, this is the thing that people might find rather hard to see. How could you have things which we can understand, but which are not algorithms? I've given you an example here. It's a very simple sort of problem. The problem is you're given a set of shapes, and these shapes are made out of squares, equal squares, glued together along their edges. So they're plane shape, something you can put on the plane, and they're made into equal squares glued together. This is a very particular example with these three different shapes. And the question is, can you use those shapes to cover the entire plane? Now, it's very interesting because there was a mathematician, a Chinese-American mathematician called Hao Wang, who, it wasn't quite this problem, but it was a closely related problem, who was trying to decide whether there was an algorithm which will decide whether or not a given set of shapes will tile the plane or not. Is there an algorithm? And he thought there was, but this depended upon the fact that if you could tile the plane with these shapes, that is to say, cover the entire plane without any gaps or overlaps, as in this example here, if you can cover the entire plane with these shapes, somehow, then you can do it in a way which is periodic. Periodic means it repeats itself again and again and again, like a crystal. It simply repeats itself. And this was a natural thing to assume. But his graduate student, Robert Berger, I think he was a graduate student, Hao Wang was able to show that there was an algorithm for deciding yes or no whether a set of shapes will tile the plane, if it were true that every set of tiles which will tile the plane will do it periodically. His student, Robert Berger, showed that this is not true, that there is a set of shapes which will tile the plane, but only the original set of shapes involves several thousand. And if you had these several thousand that he constructed, he showed that they would only tile the plane non-periodically. Now, there's a story to all this, which I won't go into, but I came across a set of shapes which I got down to two, which were only two shapes, which would tile the plane in a way which is never periodic. This is an example with polyominoes. The shape I had involved different angles, so I won't give it to you. But if you're just using the polyominoes, which are made out of equal squares glued together, then you can have ones such as this example, where you can tile the plane, and I've given you the test of how you can do it. You can keep on going forever, but it never repeats itself. This is an example of a non-periodic set of tiles. And it was shown by Robert Berger that there is no algorithm which will tell you for a given set of polyomino shapes then can you tile the plane with them or not? And there is no algorithm which answers that question, yes or no. And I'm giving that as an example to show that there are sets of problems for which there is no algorithm. This is rather surprising to people because they think, yeah, well, it's a well-defined problem. You ought to be able to find an algorithm that tells you what the answer is. This is just an example which you can understand because I can give you, as I say, like this example here, that there is no algorithm which will tell you, no algorithm whatsoever. It's not that nobody has found one yet, that you can show that there isn't one. There is simply no algorithm which will tell you for a given set of tiling shapes whether or not they will tile the plane. There are many other problems in mathematics. There are problems which look a little bit more like physics. The great physicist Paul Dirac produced one which looks very much like a non-computable problem. I don't know whether it is. I haven't given it to you here because I don't know what the answer is. But I'll give you another example of an interesting thing like this. Here we have three shapes which are just polygons, a square, a regular hexagon, and a regular dodecagon that's got 12 sides. And I've marked them in this way so that you have to match where the lines go, so that you have to make the lines fit together. And here we have the way it fits. You see, you've got the dodecagons and you've got the hexagons and the squares, and it's a completely regular pattern, but you've got to put the different shapes in here, the dodecagon in here and the square in there and the hexagon in there, in such a way that they match so that the lines drawn will fit together. And that's the problem. And the question is, how do you do it? Well, it's a non-periodic example. There is no solution which is periodic. However, there is a solution and you can do it. And just to show you the idea, this was a colleague of mine who put this on a computer to show you how far you can get. The computer doesn't decide whether you can do it or not, but if you have a procedure, it tells you how to do it. And this just shows you how complicated the shape is. The very smallest, they look like little spots. They don't look like even circles. That's the smallest shape. I guess I've got that here. That's the little tiny ring there you can see on the hexagon. Or you can take the intermediate ones or the big rings, and you can see them in my picture. I'm going the wrong way, sorry. There we go. You see bigger rings and intermediate rings, and you've got much bigger, the lines fit together in different ways. And it looks as though it might be periodic, but if you look at the next one, you see it filled in a different way from this one because of the details, and it never repeats itself. Now, this is just to show you that there are examples in mathematics of problems which are not computable. So my idea was, because of the Gödel theorem, there has to be something that enables us to do things which are not computable. Because this is telling us it's got to be something which isn't an algorithm, because otherwise you're stuck with the Gödel theorem. Now, I wanted to tell you about quantum mechanics. I've got a blank slide here because I realized I didn't want to go into the details of it. The only thing I want to tell you about quantum mechanics, you see, I thought a bit, I'd learned from a lecturer when I was a graduate student by the name of Steen. He told me about Gödel's theorem. I learned about general relativity from Bondi. I learned about quantum mechanics from Dirac, the great physicist. So I had these sort of ideas about how physics worked as we currently understood them. And I couldn't see anything in the way it works, which could be non-algorithmic. But I needed something in physical laws, which were something you couldn't put on a computer. At that time, it was difficult to see how you put Einstein's general theory of relativity on a computer. But much later, people saw ways of doing this. And in fact, we know this. And we have this wonderful gravitational wave detector called LIGO. And LIGO can detect signals from black holes spiraling into each other. And these very specific signals can now be worked out very carefully using computers. So you can see, using Einstein's general relativity, you can certainly put that on a computer and try to work things out. So that means not just Newtonian mechanics, not just Maxwell's equations for electromagnetism. These are all things you could put on computers. There was some little problem about whether you have to get infinite precision, or is a finite amount of precision good enough? I don't want to go into that because it is a technical problem, but let's ignore that problem because I don't think it's the answer. I want to give you something else which I do think is the answer. And this had to do with the lectures I went to by Dirac, who told me about quantum mechanics. And he was explaining in quantum mechanics, you can have, say, a particle, let's say a proton, which could be here, or it could be there, or it could be here and there at the same time. So you can have states in which the proton is not in just one place, but it could be in two places at once. And then he took out his piece of chalk and started talking about his piece of chalk being two places at once. Unfortunately, at this moment, I was staring out of the window thinking about something completely different, and I missed his explanation of why his piece of chalk could not be in two places at once. And when my attention came back to his lecture, he'd moved on to the next thing. So I puzzled from then on, ever since, what on earth prevents a piece of chalk being in two places at once? It's probably just as well that I did not hear Dirac's explanation, because it was presumably some way to tell you not to keep worrying about this problem. It was probably a calm down kind of explanation to tell you why you didn't have to worry about it. And I think it was a good thing, but I didn't get calmed down because it's a serious problem. Now, you see, the two things I want to say about quantum mechanics are, first of all, the Schrodinger's equation. It's a wonderful equation. And this tells you that the quantum state, now what's a quantum state? Well, it's a thing, how you describe what's going on. I don't want to talk too much about the state, except that I will say something about it in a minute, but it's usually written by the Greek letter psi. We haven't yet got down to psi in the COVIDs, I'm afraid. I hope we don't, but maybe we will at some point before too long. The Greek letters we seem to have got as far as Omicron, and I'm not sure when we get to psi. But psi is a Greek letter which is usually used for the, I'll show you a psi because I want to go to this anyway. Here's one right up at the top, that's a psi. And that psi represents the quantum state. And the Schrodinger equation tells you how this psi evolves with time. So if you know what psi is now, and you plug it into the Schrodinger equation, you can put it on a computer if you like, it tells you what psi will be in 10 minutes or 20 minutes or half an hour. That's what the Schrodinger equation tells you. The only problem is that it tells you something rather absurd because you don't quite know what to do with this quantum state. So what you do is you measure it. So you wheel out of the cupboard your measuring device, and your measuring device measures it. It's not quite clear what that means, but it measures it. And what it tells you is your psi might do this, or it might do that, or it might do the other thing with certain probabilities. Now, the Schrodinger equation doesn't do that. It just tells you in a deterministic way what psi does, how it evolves with time. And it's a very clear-cut, beautiful equation, which tells you what, all you have to know is the thing called the Hamiltonian. The Hamiltonian, I won't go into this at all, but the Hamiltonian is really telling you what the energy of the system is. And it tells you what the energy is expressed in terms of all the parameters of the system. So you have to see, how does the energy depend on this? How does it depend on that? You just put all those things in. And if you know what that Hamiltonian is, then Schrodinger tells you how the psi evolves. Now, the trouble is, it doesn't tell you why your piece of chalk is not in a superposition of in two places at once. You could make an experiment. Well, Schrodinger, in fact, himself described a hypothetical experiment just to show how absurd his own equation is. He described an equation where you could put a cat in a box, and according to his own equation, that cat would evolve into being dead and alive at the same time. So he said, well, you just follow my equation. I say my equation, that's Schrodinger talking. Follow Schrodinger's equation, then the cat becomes what's called a superposition as being alive and dead at the same time. Now, Schrodinger was not giving this example to say, well, that's a challenge for you guys. Can you make an experiment which makes the cat dead and alive at the same time? Some people regard it as a sort of challenge. I don't think that's what Schrodinger was doing at all. I think what Schrodinger was doing to say, look, this is absurd. That is not the way the world operates. Cats are not dead and alive at the same time. There is something wrong. Now, it's very curious. You find that some of the mathematical physicists took the Schrodinger view, something is wrong. Einstein is most prime example. He said, look, there is something wrong. You've got to get a better theory, which tells you what happens. It just, see, the trouble is you wheel your apparatus out of the cupboard. Why is that piece of apparatus not following the Schrodinger equation at all? Because it doesn't tell you, yeah, the piece of chalk is either here or over there. It says, okay, this piece of chalk is in the superposition of being here and there, and therefore my measurement is in the superposition of measuring it as being here and of measuring it as being there. You could go and put your piece of apparatus and looking at the cat, and it would be in a superposition, a little dial, if you like, that says cat alive, and the dial we're saying cat dead, and the dial would be in a superposition of being in live and dead at the same time. It never becomes dead or alive. That's what we see in practice. So following the Schrodinger equation doesn't tell you what happens. What you have to do what's called collapsing the wave function. And this is what physicists always do. They say, okay, well, you've got to collapse the wave function. Collapsing the wave function means you don't think of it as a superposition at all. You just say it's either one thing or the other thing with certain probabilities which you can calculate from the wave function. But when do you do that? When do you collapse the wave function? There's nothing in physics which tells you that. Well, many physicists would say, well, it's a conscious observer which comes along and looks at the state, and that conscious observer, by the very process of looking at it, makes it become one or the other. Other physicists say other things about it. Some physicists, it really does both at once. And the conscious observer, you've got two copies of the conscious observer. You might be one of them or you might be other. I've never understood that one, but that's the sort of thing people talk about. Now, I want to describe that in the form of a sort of cartoon here. You see, this is a wave function, and I've got it at the top of the page, and it's rather small because it's a small wave function. What do I mean by a small wave function? I'm not sure what I mean, but what I sort of mean is it's talking about small things, about atoms or something like that. It's not talking about a whole piece of apparatus. It's talking about something small. And it's floating around freely, happily following the Schrodinger equation, and it's small. Now, when it gets big, this is the problem. You see, there's my next picture. When it gets big, and I'll have to make sure I can do that. Well, here I made it big, you see. You have to have all these different props keeping it up. And I've got the names of various people. This is Wigner, who had certain ideas about how maybe your consciousness might collapse it to be one or the other. I've got Bohr, who's had other ideas. I've got von Neumann, who had ideas about introducing what are called density matrices and things like that, which are just a way of putting off the problem for a while. It doesn't really solve it. And Everett, who considered that the wave function never collapsed and all these different worlds are coexisting. It doesn't really explain anything. It doesn't say why we only observe one world, but that's a different point of view. I'm just saying that there are all these ways of keeping the wave function sort of propped up. So somehow you keep following the Schrodinger equation and you have these different ways of propping it up, even though it's big, but it collapses nevertheless. So this is my cartoon, just to show that it really doesn't help. None of these different ways of wriggling around and trying to preserve the Schrodinger equation doesn't help. It collapses anyway. So the wave function does collapse, and I'm saying it's not a question of who looks at it, and I think you can make a good argument why that cannot be the case. It's very hard to make it. You can say the observer can be, I have an example where you might have a planet, you see, a long way off, and its weather is a superposition of all different weathers because there's no conscious being on that planet, and so the wave function never collapses according to that theory. And then you send a probe out and it looks at the weather. It's a superposition of all different weathers. The signal comes back to the Earth, and some conscious being looks at the screen and suddenly it collapses because that's the first time any conscious being has looked at this weather. Seems to me that's an absurdity. There is something out there in the physical world which is governing when the collapse happens. It's not consciousness which is doing it. Now, this is the point of view I'm adopting, and I want to say that I think it's to do with gravity. Now, you see, gravity is a very interesting phenomenon, and there's no reason, according to current views, why you shouldn't apply quantum mechanics to it. But that's the interesting question. However, gravity has a very curious feature to it, which is unique to gravity. And here I have Galileo or somebody dropping a big rock and a little rock from the Leaning Tower of Pisa. And as Galileo very clearly explained, if there were no air resistance, he knew about the effect of air resistance. If there were no air resistance, the big rock and the little rock would fall together. And so an insect sitting on the big rock, looking at the little rock, would say, oh, there's no gravity. So if you fall freely with gravity, it disappears. And in the bottom picture, we have an astronaut and some futuristic space station up there, 2001 type of space station. And this astronaut floating freely. There's the Earth. So you might say, why isn't the gravity affecting the astronaut? Well, it is if you like, but the gravity is cancelled out by falling freely with it, this astronaut in orbit. So that's the key point about gravity. It has what's called a principle of equivalence. You can get rid of it locally by falling freely with it. And the point, I don't want to go into the technicalities here, but let me just describe it, because this is an argument which I made some years ago to try and show that this principle of equivalence, which I've just indicated in this previous slide here, the principle of equivalence is inconsistent with what's called the principle of linearity of quantum mechanics, which is telling you that superpositions will persist. So that's Schrodinger's cat, that the cat will be alive and dead at the same time if you follow the Schrodinger equation. So the principle of superposition and the principle of equivalence are inconsistent. Then this is just a little bit of an equation to show you how it works. You imagine an experiment done on a tabletop. I won't go into the details because it's a bit technical. Down on a tabletop, and you want to consider you want to consider the Earth's gravitational field as part of your Hamiltonian. And a normal physicist would say, well, you just put a term on the Hamiltonian and you get a certain wave function. But then you say, well, Einstein would say, no, 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 no. What you should do is fall freely, and then you get rid of the Earth's field, and then you get almost the same wave equation, but it's not quite the same. And the critical thing is it's not quite the same. It's what's called being in a different vacuum. And this crucial thing about the different vacuum, when you do a calculation, and I'm not going into that here because that's not the level of talk I want to say. I'm just saying there is a calculation which shows you there's an incompatibility between the principle of equivalence, that is to say freely falling with gravity and it disappears, and the principle of superposition in quantum mechanics, which is really the Schrodinger's cat thing, which says that the superpositions persist and you can't really unsuperimpose them, at least in general you can't. So that what you're having is these two principles basic to both theories, and they are not consistent with each other. And the only way of really resolving them is you see that there's a sort of problem between the two, and this problem gives you an uncertainty in the energy, and this uncertainty in the energy tells you that the superposition, which I've imagined here at the bottom, I've got a lump of material. It's not just the Earth field I'm considering now, but in this experiment, I'm putting a lump of material into a superposition of being like Dirac's piece of chalk into two places at once. So it's in here and here at the same time, and there must be some uncertainty in the energy of this system. And then you use Heisenberg's time energy uncertainty, and it gives you a lifetime for this system. So it's telling you that this superposition of being here and here at the same time only lives for a certain length of time. For a big lump, you can see like a thing like this would be a very, very short period of time. If it's an atom, it's probably longer than the age of the universe. But you could imagine experiments being done which could try and see if this is right. So far, no experiment has yet decided on this. I was hoping that Dirk Bouwmeester, he's a Dutchman who has been working on this problem, would by now have an answer. He ran into some problems about having to get the thing very, very cold, which is one of the little problems here. There are other experiments which could be done involving things called Bose-Einstein condensates, and I have a colleague, Yvette Fuentes, who is working on this type of problem. I think it's the most important problem in current theoretical physics to see whether you can measure an effect like this, which will tell you a superposition between macroscopic bodies like this will have a certain lifetime, and it becomes one or the other in that lifetime. Fascinating to see if this is true. Okay, now what's this got to do with consciousness? I was looking for a place where the Schrodinger evolution is not followed, that's computable process. You want something where there is a chance of something happening, which is not computable. Now, when I wrote The Emperor's New Mind, I tried to learn enough about neurophysiology to see if I could understand how there could be something non-computable in the operation of the brain. And I learned about nerve propagation, the I got myself confused. Huxley-Hodgkin theory of nerve propagation, and I learned about that. I thought, there's no way you can preserve the coherence in such a system. I didn't see how you could possibly harness whatever is going on in the collapse of a wave function. You see, my point of view is the collapse of the wave function is a physical process. It is something beyond our current physics. It's something which comes up when you correctly combine general relativity with quantum mechanics. It's where quantum mechanics breaks down, in a sense. It's where general relativity imposes itself on quantum mechanics by its own principles have to be taken seriously and accounted for within quantum mechanics. This is not quantum gravity, which lots of people try and play with. That's the other way around, where you're trying to apply quantum mechanics to general relativity. That's a tough problem and not really very close to what we need here, because that is concerned with energies or tiny distances or something way, way off the scale of anything one could possibly measure these days. However, the other way around, how does gravity affect quantum mechanics? That is not so far off what we can achieve with experiments right now. So I'm hoping that such experiments will be performed within the next few years, and will maybe demonstrate something like the collapse of the wave function is a real physical process which takes place at a certain level. Now, what could this have to do with consciousness? So my argument is that you've got to look at something which goes beyond the normal kind of computable determinism that we have in ordinary physics, and something where you have a non-computable action. And this non-computable action, the only place I could see that happening is in a physics of the collapse of the wave function, which we do not yet have. And this is certainly the argument I made in The Emperor's New Mind, but using not quite the right criterion and so on in Shadows of the Mind, I do use what I consider to be the right criterion. And I also consider these things microtubules. What are microtubules? Well, you see, I didn't know about them when I wrote The Emperor's New Mind. I wrote that book and people didn't quite see where I was getting at, I suppose. I didn't see where I was getting at because I couldn't see a place for something where you could see the collapse of the wave function playing a role. It didn't stop me writing the book. I sort of put something down I didn't quite believe at the end. But Stuart Hameroff, who read my book, and he said, I think you should know about something about microtubules. This is a much better role. His job was to put people to sleep. That's not quite the right word, but using general anesthetics. And he was interested to know, what do general anesthetics actually do? And he came to the view that they affect microtubules. These are, I've got in these pictures, I'm trying to show you, here we have nerves, and here we have a synapse. And inside these nerves, we have these microtubules. And the argument is that they could preserve coherence, whereas just to do this with ordinary kind of circuits and ordinary nerve propagation isn't going to be good enough. You've got to have something maybe which controls the strengths of synapses in some coherent way, which is making use of quantum states within microtubules. And I was impressed by the sort of symmetry they have. They're very, very symmetrical looking structures, and also tubes, so there might be something going on inside the tube which could preserve quantum coherence. Stuart originally had the idea that maybe these tubulin proteins, the little dimers which construct these microtubules, and then they might have different, I don't think that's his view now. It's developed in very interesting ways, which I really haven't got time to describe. But I think the theory has moved along very considerably, mostly in the area of the neurophysiology. And there's a certain level at which there are a lot of microtubules in these things called pyramidal cells. He argues that it's not most cells which are important here, but the pyramidal cells are the really important ones. And this is just something which I do describe in The Emperor's New Mind. And I don't think I have time really to talk about this. But when you go into this theory further, it does seem to relate to something which is in The Emperor's New Mind, where I talked about experiments due to Benjamin Libet. And I just quickly say something about these experiments, because in these experiments, a patient who had needed a brain operation for some other reason, Benjamin Libet took the advantage, and with the patient's permission, of course, to do an experiment where he would have an electrode attached to the patient's finger and another electrode to that part of the brain which was responsible for the sensation in the brain of the finger being activated. So, and these different signals I have here, the point I really want to make is that if the electrode indicates this top one, you see, it happens at a certain time, then according to the patient feels it pretty well at the same time, just almost immediately afterwards. Whereas if the brain part is stimulated, the feeling comes much, much later, about half a second later. And here we have, a little bit further down, if you stimulate the finger first and then stimulate the brain, a quarter of a second later, the finger stimulation is not felt. Now, how can you unfeel something which happened earlier than something that happens later? Very, very peculiar. I don't want to go into this in detail, but in The Emperor's New Mind, I discuss a possible explanation of this, which was that somehow one's actual perception is delayed later on. But then you have a problem. If the perception is delayed, how do you do things very quickly? And it was not until much, much later that I had ideas about this. And here we have a thing. Time is going up the picture, and here we have a body which is put into a superposition of two places at once, and then it collapses, it becomes one or the other, and then from there on it becomes one. And you have problem with relativity if one of them happens and the other one doesn't. So this picture was to try to say that you have problems with relativity unless the choice is in some sense made right back at the beginning, which looks crazy, but that is sort of the view I hold here. So this is a picture, a cartoon of my view right now. It's a crazy view, but I think that there is some sense to it. Let me just try and explain this. This is the last thing I want to show. At the bottom of the picture, we have a laser shooting a photon at a lump here. And it's supposed to be hits it hard enough that it will move the lump because it's a really energetic photon. However, in between is what's called a beam splitter or half-silvered mirror, which half reflects it and half transmits it. Because you can do that in quantum mechanics. You can have a half-silvered mirror, if you like, which transmits half the light, reflects half the light, and it does this to every photon. So every photon, the state is split into going horizontally and going down. Now, if it goes horizontally, it hits a lump. Now I've got to have time moving up the picture. As the lump is hit, it's put into a superposition of being hit and not hit because of the beam splitter here. So it's hit and not hit. And as you move up the picture, they get further and further apart. And then it gets to a point where it's got to collapse one or the other. And this is to do with where the conscious effect is. That sort of happens later here. The consciousness has to do with, you see, Stuart and I were saying, is that consciousness that the collapse of the wave function produces consciousness? I didn't like that because these things are happening all the time, all over the place. We call it proto-consciousness. Proto-consciousness means, roughly speaking, the building block out of which consciousness is constructed. So it's a different thing. If you don't have proto-consciousness, you couldn't have consciousness, but it's not consciousness yet. It has to be built. The building, if you like, has to be built out of proto-consciousness to make it genuine consciousness. Orchestrate is the word used. It's a bit vague what we mean by that, I'm afraid. It has to be a bit vague at the moment. Maybe someday we will know what we mean by that. But somehow the proto-conscious bits have to be brought together, and the consciousness, if it's a big enough thing, decides whether it goes one way or the other, if you like. But the choice goes right back to the initial thing. So it's like the previous picture I had, the choice, even though the collapse comes up here, the choice is as though it had been made here. It's a difficult idea to get your mind around, but it seems to be that you need to do that. In order to understand it, I introduced two different ideas. One is the quantum reality, in which the choice is still there right up to the end, and the classical reality, which follows one branch or the other. So the classical reality doesn't branch, it's one or the other. The quantum reality remains in this kind of superposition until the choice is made, one or the other. It's clearly not a very complete theory at the moment, but that's the way we're going, and we're trying to understand very curious things about the way consciousness does seem to operate, which need an explanation beyond what we seem to have at the moment. And it's not just the argument which I was making about non-computability. There are other curiosities, and I think we need to understand better what's going on. And my own view, and Stuart Hameroff also, is that it has to be the objective collapse of the wave function. So we call that OR, objective reduction of the quantum state. And it spells OR, of course. It says it's one or the other. And that orness comes about once the thing is big enough and it becomes one or the other. But that one or the other has to be orchestrated in some way. And that's what we call it, orchestrated objective reduction. The orchestrated is not really very well defined, but it somehow has to mean something, whether it does one or the other. It's obviously a long way from a very broad understanding of what's going on, but it relates to the sorts of things which produce anesthesia. It relates to things and experiments that people have done. And I hope that they will do more experiments which will relate more and tell us whether we're wrong or right in the way we're thinking about the way consciousness operates. A lot of this is described in Shadows of the Mind, not the picture I'm showing you here, but certainly the objective criterion, the microtubules are talked about, and the particular criterion of the collapse of the state is described in that book. So most of it's there. Thank you very much.
Thank you very much, Professor Penrose, for this very interesting talk about these fascinating topics. So now we have time for a couple of questions. I'm going to start with a kind of a personal question. And the question is the following. When you are a scientist, you have the freedom to decide what to study. So I'm curious to know why did you decide to tackle this difficult problem of consciousness from a physical and mathematical perspective? And if I mentioned this in the introduction, maybe you didn't understand because it was in Portuguese, but I know that your father was a famous geneticist, I think.
Yeah.
And also I remembered reading your biography that at some point you consider going to medical school. So I just wonder if this has something to do with or the reason that you choose to work and study this topic.
Well, it's a difficult question because I didn't decide to work on this topic. It was more that I was curious about lots of things. And certainly my father's interest in, well, he was interested in the heredity of mental disease. That was me. And he was, Down's disease was one of the things he was particularly concerned with, but lots of mental disease. And he certainly had a very, I mean, he didn't know about the point of views that I was having here because these were developed really later. Not, well, not sure how much of it I thought of earlier, but I certainly wasn't taking these ideas very far at the time. When I was a graduate student, as I mentioned in my talk, I went to these lectures by Steen and by Dirac and Bondi, and they were not what I was doing. You see, when you ask what did I decide to do, I was doing algebraic geometry, which is pure mathematics. And so that's what I thought my career was going to be, in pure mathematics. But I learned a lot of physics from Dennis Sharma, who was a good friend of my brother's, and he had taught me about cosmology and about things to do with Mach's principle, and various things to do with physics. I learned a lot of physics from him, and I found it very exciting. At that time, the steady state model of cosmology was going along, and Dennis was a great promoter of this theory, but eventually that got shot down. And I was a very great admirer of Dennis because when that theory got shut down, he changed his mind. Not so often with physicists or scientists that they will actually publicly say, I was wrong. So you don't get that often. He did. He was very clear on that point. So that made a big impression on me. You're asking me, why did I? You see, it was really the collapse of the wave function interested me a lot since Dirac's lectures, because I just had, I didn't know what was going on there. I couldn't make sense of it. The fact that it was gravity took me quite a while, I'm sure. The lectures on Gödel's theorem, which intrigued me a lot, and I was puzzled by that. It seemed to me there had to be something non-computable about the way the laws works. I'd had no idea really for a long time what it could be. It was more, I think I wanted to, I don't quite remember why, I wanted to write a popular book, but I thought this I wouldn't do till I retired. That was what eventually became The Emperor's New Mind. But I think I was stimulated by some radio talks given by two, what you might call strong AI people. This was Marvin Minsky and Edward Fredkin. And they were talking about two computers communicating with each other. And they were saying, as the human being walks up the room to where the computers are, they have already communicated more ideas to each other than the entire human race had ever communicated. And I thought, well, I see where you're getting this from, but I don't agree with you, because I think there's much more to it than just communicating. It's communicating understanding, and understanding is not a computational thing. So I formed that view. And so I thought, well, perhaps I will write a book. And I wrote this book partly at the same time as Stephen Hawking was writing his Brief History of Time. And he'd got, what's his name, this science educator. Oh, it's gone out of my head for the moment. I decided I would get Martin Gardner to try and write an introduction to my book, which he did. And then I thought people might pay attention to it. So that was The Emperor's New Mind. And then when Stuart Hameroff read The Emperor's New Mind, and he said, look, you evidently don't know about microtubules, they might be a lot of help to you. And so then we got together, and Shadows of the Mind came about as a consequence of my arguments, or partly with my complaints with people who misunderstood the arguments in The Emperor's New Mind. So I had to try and address what I thought were misunderstandings, and it's full of those things. But also it talks about the microtubules, and maybe that's the difference, that you really have to have something which preserves quantum coherence. But you see, it wasn't that I decided to do medicine or something. My parents wanted me to do medicine because they had both been medically trained. My older brother was obviously going to do physics or something. My younger brother was going to play chess, so he became British chess champion. I have to say, he just died today, unfortunately, so it was a very sad occasion.
I'm sorry to hear that.
This messenger, he's been very ill, so it wasn't a huge surprise, but he really had a wonderful, gone on a very, very long time for being ill, but he hadn't played chess for quite a long time.
So my condolences.
I had two very talented brothers, I may say.
Okay, so I'm going to read another question from the chat.
Yes.
So have you changed your understanding of the matter in any way since the original release of Shadows of the Mind approximately 20 years ago?
Yes. Oh, sorry, say that again. What was the question? Sorry.
So, sorry, the question is, have you changed your understanding on this matter, I guess, of consciousness in any way since the original release of Shadows of the Mind approximately 20 years ago?
Oh, sorry. Yes. I would say yes and no. The no means I still believe more or less what I said there, that it's probably microtubules, which are the main place where you have coherence, quantum coherence going on. It may not be the only place. I think it's quite likely there are other structures in the brains also which are acting in concert with the microtubules. I think there were clathrins. I'm not sure whether I knew about the clathrins at the time I wrote that book. But the main changes are to do with where you find consciousness. You see, Stuart Hameroff has the view nowadays. You see, one of the things that was very curious, even in writing the Shadows of the Mind, or the Emperor's New Mind, which puzzled me, was the difference between the cerebellum and the cerebrum. And in fact, at that time, I didn't even know what seems to be known now, is that there are more neurons, considerably more neurons in the cerebellum, this part at the back and underneath, than there are in the cerebrum, this main part that we think of as the brain. The cerebrum seems to be where consciousness resides. The cerebellum seems to be entirely unconscious. the cerebellum is organized much more like a computer. There's no crossing over. It's directly connected with things. It's more like a computer, but it seems to be entirely unconscious. It's got more neurons in it too. The cerebrum, this part, the main big part, seems to be where consciousness comes about. And more specifically, it's very likely to be in this layer. I think it's 4 layers down. I can't remember exactly, where you find these pyramidal cells. They're particular cells which have lots of microtubules. There are lots and lots of microtubules, and they're organized differently from in other cells. So they seem to have a very different role to play. And the thing which is different in my current understanding has to do with what I was saying at the very end, to do with the timing. And there is something very curious about how the classical reality is somehow controlled backwards from the quantum perception. And so there can be this delay. What I described in the Libet experiments in the Emperor's New Mind, I think is quite correct. I've never heard anybody refute those experiments. They're not discussed much because people just brush them under the carpet. But I think there is something very curious going on about the perception of time, which can be understood only with this quantum classical reality picture, where somehow the classical reality propagates back. And so actions can take place much more quickly than you might have thought. That somehow the superposition is there, prepared for one thing or the other, which it is somehow consciously controlled in a way which kind of violates one's normal ideas of ordinary propagation of things in time. A very curious thing, which I think we need to understand more. But in order to understand certain paradoxical things in neurobiology, I think we're driven in this direction. But that's very much for the future.
Thank you. So I think we are running a little late, so I'm going to read the last question that comes from Gésio Gutierrez, who is the president of the foundation, Editora Unesp.
Okay.
And I cut his question a little bit short. I think it has to do with testing these models. So we know that physics is an experimental science, basically, so it has to be tested, theories have to be tested and verified. And I think Gésio is asking if there are other models that can also be used to explain consciousness, and if these models can be testable.
Well, there's certainly lots of models of consciousness. I wouldn't start to say that this model, this is certainly a minority view, because, well, I think largely because the physics is not something people who work on neurophysiology don't know much physics. And I'm talking about physics beyond what we currently understand. So when you say experiments, there are 2 classes of experiments. One is the physics experiments. They haven't been done yet. We need experiments to test whether the collapse of the wave function actually is in accordance with the sort of view I'm putting forward or not. And that is a genuine experiment, a class of experiments which have not yet been performed. I think within the next 5 years, they could be performed. And I hope they will be. I don't see a great movement to try and test this. You see, people don't try to test the collapse of the wave function. I don't think that most physicists try to get you they use one of these props of having the thing propped up in the way I had in that second picture I used in the cartoon, the 3 pictures. I don't think they believe that collapse of the wave function is a real physical phenomenon. So that needs to be tested. That's pure physics. The second part is, how does this relate to biology? And there are experiments, not going very far as yet, to see what it is that general anesthetics actually do. Do microtubules actually propagate information in neurons? And there are experiments involved here which are interesting. And I think it'll be a long while. And I don't see any experiment tomorrow giving us an answer to these questions. But there are experiments. And these experiments are partly looking at microtubules, looking to see whether they propagate information, whether they propagate quantum information. Is there something quantum mechanical, essentially, in how they persist? is there something which could involve the collapse of the wave function and what they do? But that involves, as I say, classical physics experiments as well as biological ones. So we need both. And we haven't any definitive answers as yet. Some interesting preliminary answers, but nothing as yet, which we can definitely point to.
Yeah, thank you. Thank you. So just a comment. When I was preparing for this introduction today, I came across a paper that was in the archives a few days ago by a group of physicists trying to test the gravity-related wave function collapse in underground experiments in Gran Sasso.
Oh, I know the one you mean, yes, yes.
And that part of the group is, you know him, Dyoshi. I don't know how to pronounce his name, Lajos Dyoshi, yes. Who has also a model similar to yours of gravitational wave collapse. So this is, I was very interested in that these people are actually testing, looking for signatures for this type of models of gravitational collapse of the wave.
Yes, I should make a clear point about this. There is a model which they call the Dyoshi Penrose model. Now, you see, Dyoshi, before I did, had the same criterion of the rate of collapse to the one I have. So that's why it's called the Dyoshi Penrose model. Apart from that, the models are very different. You see, my model says, it's like in this picture, this last picture I'm showing, where the collapse somehow retroactive. You see, the experiments that were done in this tunnel have to do with a heating phenomenon. The idea is that this collapse is going on all the time, and this in effect makes the molecules or the atoms move around effectively as they collapse. It's as though they heat. And so you have a heating process taking place. Now that's what you have in the Dyoshi model, because it's a more, what you might call a sensible model, that the collapse happens now. Whereas my model, the collapse, it's in a certain sense is retroactive. It's as though it had happened earlier. And so you don't get the heating. So the fact that you don't see this heating phenomenon really argues against the class of models in which the collapse happens now, if you like, but not the kind of model in which the collapse is as though it has happened earlier. It's a little bit harder to understand that class of models because they seem to, at first sight, they seem to violate causality. So you have to make clear that they don't violate causality. It's a curious way in which the classical and quantum realities interrelate to each other. So it's not violating causality, but it does give you an effect which wouldn't give you the heating. So I don't expect to see the heating, and they don't see the heating. I think there will be other experiments like astrophysical experiments, such as with neutron stars and things. Would you get effects where you would see spontaneous heating there? It's very interesting. I mean, I don't think the spontaneous heating takes place. To me, this would violate general relativity because you would have to have the spontaneous heating would go against the Einstein equations. So I'm very much against that as a picture. But to make it work without the heating, you've got to have a crazy model like the one I'm suggesting, which has this sort of retroactive classical reality, as opposed to the quantum reality, and they sort of diverge from each other in a way which needs a book, which I'm trying to write. At least I sent out some notes to people, not intending to write a book, but then I realized it really should be a book. But the trouble is then getting the Nobel Prize sort of killed it off. And so I haven't done anything on this book for a year. I'm hoping I can get back to it.
So we can blame it on the Nobel Prize, okay.
I think so. Well, that's my excuse.
Professor Penrose, it has been an honor to moderate this event, and in the name of, on behalf of the Editora Unesp, who is publishing her book in Portuguese today, I'd like to thank you for giving this wonderful talk. I hope the public audience recognize the value of curiosity-driven science, and this is hard science. You have a theory, you have to be very serious about modeling your theory and make predictions. And this is a fantastic example. So thank you very much. And I think we can we can stop here. I don't know if Sabrina wants to say a few words or Jézio before we finish.
Okay.
Or should we just disconnect?
I don't mind. I'm happy if anybody wants to say anything.
Jézio, you want to say some things? Anything?
Yes, well, eu gostaria agora para o grande público, se em primeiro lugar eu gostaria de saudar.
Well, first of all, I would like to salute this partnership that Dyoshi and Unesp have created to make this meeting possible. Professor Penrose.
Your availability, your generosity, and your brilliancy in the development of this event. I think that this is an honor, as Rogerio has just said, and we hope that your presence in Brazil is not limited to this event. And I hope that other events in the future, in the near future, could be promoted with your presence as well. Thank you so much again. And now I pass the word to Eduardo to finish the works here. Thank you.
Thank you very much. My pleasure.
Sir Penrose, it's an honor to be part of everything. It's an honor to be close to such a special group. And I hope that we can bring you to Brazil in a very near future. Thank you for everybody. Thank you for Professor Jézio, Professor Rosenfeld. It's been an honor to be part of this huge event for us too. Thank you very much for all.
Thank you.
Thank you.
Okay, goodbye.
Bye-bye.